Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. So we'll have to try and understand why this is called Demon's algorithm. So the idea behind that is that for medical images we usually have these edges of these organs or anatomies or features of interest, and these are actually isocontours. Right? We saw that I showed that in the previous video. Okay. Now, if we have these contours, then on the boundaries of these contours, we can position these so-called demons, like shown here. Okay. These are just points on the contour. Okay. So in this case, there are two contours. One is in as the author calls it, the scene, and the other is the deformable model. The scene is basically the fixed image, and the deformable, the model is the moving image. So we need to denote them by F and G respectively, right? So the idea is, we can sample the entire image. We have the pixels in a picture in a medical image. We can look at all the pixels, or we can just look at the edges. Edges are easily obtained by edge detection, and we can choose points on the edges. We can find the edge and do the points on the edge. Or if you have a segmentation, we already know where the edges are. Okay. So then we position these points. We have these grid points. You call them control points or the demons points, right? Okay. So why are they called demons? Because there's a very similar concept. When say similar concept, the demons concept was introduced in physics. The idea is if you have like a semi-permeable membrane. So for instance, something like a membrane here, and then you have different types of molecules, okay, A and B, circles and crosses, and then there are these demons sitting here. Because it's semi-permeable, you can go in this direction, which tries to separate out, just the A and from the B. So basically, on one side you have the A's, the other side it only lets the B's through. So after a period of time, you will have one side of the permeable membrane, you have all these X's. The other side, you have these O's. And it turns out that this is in violation of the second law of thermodynamics, right? But then it turns out that that's addressed by considering that the demon needs to consume energy to sort these, right? Because this from here to there corresponds to a decrease in entropy, which simply cannot happen. So the idea of this demons is exactly what he uses here. So he calls these points on the contours of objects of interest as demons, and they serve the purpose of the demons, that is basically to decide, to push objects inside or outside. So we'll see that in the next slide. So if you look at this picture, this corresponds to what the demons algorithm does, right? So the scene here is nothing but the fixed image, F, and this is the moving image, G. Okay. So you have the corresponding points, right? So you have these dark spots here, which correspond to your demon points. And then, of course, we assume that, when you start out at the first iteration, there is some degree of overlap, right? So if you look at this, all the points in the scene or the fixed image that are inside the model image or the moving image contours, they tend to push inside, while those which are outside the model tend to push outside. Okay. So this is kind of like trying to squeeze your moving image into the fixed image, correct? So the demons decide which points to squeeze in and which points to squeeze out. So that's why it is called the demons algorithm, because these control points or the demon points, as you can call them, decides, what piece of the model comes in and what piece of the model stays out. Okay. So he has provided some fixed examples. So for instance, if you look at this example here, this is basically the second row. You have all these spikes basically show your, hold on one second, sorry. These spikes basically show here, these ones. They show your gradient pointed along, which is basically it's pulling outward, except in the region of overlap here, this region overlap here, where it's actually dragging the other disk inside. So you're trying to match these two disks, right? So this is the moving disk right here. This is the moving disk, and this is the fixed disk. So the fixed disk, initially all the gradients are pointing out, and the regions which are overlap, basically that is the fixed image is inside the moving image. You try to drag the moving image inside. So you see the first few iterations wherein if you can call this as the moving image, kind of diffuses into the fixed image, right? So you can do that, and of course, depending on the orientation of the gradient, say how do you decide how to push, when you should push in, when you push out, it depends on the orientation of the gradient, right? So for instance, how do we decide? The daemon in P pushes the model image according to gradient of f, if f of p is less than g of p, and you see here, okay, let us see this example. So it's completely done. So here it's been completely moved in, and as the author states, according to Beginner's gradient of f, if f of p is greater than g of p. Okay, so there's another figure which actually tells you that, for instance, this right here. Okay, so the model in G is pushed by the daemon according to gradient of f. Again, so f and G are these intensity contours you can think of, in any dimension. If f of b is less than g of p, then you have pushing to the right according to this picture, right? And according to minus gradient if f of p greater than g of p. Okay. So this is the simple tool that can be done. Okay. And we saw this one implementation is what we saw earlier in terms of the Horn-Schunck flow, where we then made the constraint on V to be along with proportional to gradient of f. Then we derived an expression for the update scheme. Okay. So the idea, so he also describes how this is actually to be implemented. Yeah, so here's the explanation for the iterative algorithm. So at each iteration I of this process, so we saw where at each iteration we have to estimate the velocity v. So G is the, in this case, G is the moving image, which he calls the model, and F is the scene image, which is basically the fixed image. And G subscripts I are nothing but the image G defined by the current transform Ti. So I is the iteration index. So we start with the identity transform and we look for a transform Tn such that Gn, which is after the application of transform Tn to G, Gn is the image we get, so that Gn is most similar to F. Okay, N being the number of iterations, so it is the hyperparameter you fix. Okay, so each iteration I is decomposed as follows, right? So for each daemon in P in F, which is in this case, in many of cases, the daemon P is basically at the point P, and it's basically all the pixels in the image. Okay, or the most relevant pixels in the image. So sometimes there's a lot of black space around the image. Here you can crop that out in both the moving and fixed image, and you can just use whatever is remaining. So most of the pixels in F. So for all the control points, or what I call control points, daemon P in F, compute the pushing force of the daemon. Okay, according to the local shape Gi at P. Okay, so because how do we do how do we know what is the Gi? Because initially the transformation is identity, so you start off with the rough image. So you just have look at the corresponding, you assume they are in correspondence, and then you just work with that. Otherwise, you have to calculate the inverse t inverse of p. So for every pixel in f, this is very similar to what we saw for rigid body. So every pixel in f, you figure out the corresponding location in g, and you use that to calculate the force. Okay, the force in our case, we actually don't do the force. We actually directly compute the velocity, right? If you use the Horn-Schunck flow, you just directly get v, and we approximately say that since delta t is 1, we just use that as the displacement.